Okay guys, welcome back to my next video. I'm going to discuss, we are still on the topic of polarity of molecules. We have a polar and non-polar molecules. We are going to discuss about the dipole movement and polar molecule. Remember, when a molecule have a dipole moment, when a molecule have a dipole moment, is actually indicate the molecule is a polar molecule. That's the thing. What do I mean by a dipole moment? A dipole moment is stand for the covalent bond is made from a different atoms that have a different electronegativity, and they are the one atom attract the species, the electron, stronger compared to other one. This cause an unequivalent asymmetry in the sharing of electron. This unequivalent sharing of electron cause the attraction force a bit stronger. When the attraction force is bit stronger, they are not at the static place anymore. This phenomena is called as a dipole moment. This is what we call as a dipole moment. So chemical bonds are polar when they have a partially positive charge and partially negative charge. This happens due to difference in electronegativity. Therefore, dipole moment, for information, this is the symbol mu. Mu is the symbol, is actually a measure of the bond polarity. How polar is a bond is measured through the dipole moment. We will represent it by an arrow like this, indicate the movements of the electron or the molecules. So dipole moment affected by molecular geometry. This is important. That's why we learn the VSEPR model before we proceed with this section. So let's look one of the very good examples. We take NH3. Guys, by referring to these molecules, this molecule. Okay, so we notice, first of all, you must come up with the Lewis structure. So we notice with the Lewis structure, and from the Lewis structure, we notice nitrogen have a lone pair electron. It have a lone pair electron. So always keep in mind, when you have a lone pair electron and nitrogen is more electronegative, so hydrogen is less electronegative. So the electrons that been shared over here, it's been pulled towards the nitrogen rather than to the hydrogens. So it's indicate the electron being shared unequivalent at this particular point. So there is an attraction force toward to the nitrogen. Therefore, it is not at the static positions anymore. When it is not at the static position, that's indicate it is the mu, the dipole, is not equivalent to 0. When the mu is not equivalent to 0, so the attraction force is more to attracted toward the nitrogen. That's why this arrow indicate the movements of the electron toward the nitrogen rather than to the hydrogen. So actually this is more like a vector that we have learned in physics. So this is your resultant vector of the attraction force. So let's move to over here, guys. Another examples of a NF3. If you look at the NF3, the attraction, of course, it is well known, fluorine is more electronegative compared to the nitrogen. So the attraction force is stronger toward fluorine rather than the nitrogen. So what will be the resultant vector? This is like attraction. So the resultant vector will be toward fluorine rather than nitrogen. So this is your net dipole moment, where the mu is not equivalent to 0. So it is not at the static. So what I'm trying to say, polar bond is actually a polar molecule. Polar bond will have a mu not equivalent to 0. That is the most important part. So move to the next sections, guys. More examples, like a very good example will be a carbon dioxide. We notice, of course, oxygens over here have stronger electronegativity. It's a electronegativity, and over here again another oxygen have a higher electronegativity compared to carbon. So the attraction force, look at here, is like a bit physics. So the attraction force will be at this section on my left hand side, is attracted to oxygen. On the other hand side, the right hand side, the attraction to oxygen again. So what will be the resultant? The resultant of this is the molecule is not moving anywhere because the dipole moment has been cancelled each other. Left hand side cancel the right hand side cancel the left hand side. Therefore the mu is equivalent to 0. So this is an example of a non-polar molecule. Over here is a tetrahedral shape. Then you notice, if you really look at that, it's cancelling each other. This one will be cancelled by the one on the other side adjacent, and this one will cancel by this fluorine attractions, and this attraction force will be cancelled by this attraction force. So as we can see at the end, it cancel each other. Again the mu is 0. Therefore this is a non-polar molecule. So symmetrical molecule always are the non-polar. When you have a symmetric molecule, it is a non-polar molecule. Symmetric molecule is a non-polar molecule. Always keep that in mind. So let's move more examples. Tetrachloromethane and trichloromethane. This one with the trichloromethane and tetrachloromethane. This one CCl4, and again is a symmetric. And symmetric, the attraction force is cancelled by each side. So when it cancel out each side, the left with the right, the top on the bottom is cancel out each other. So again the dipole moment becomes 0. When the dipole moment is 0, it is actually a non-polar molecule. On the other hand, here it is a bit different. Of course, the left hand side and right hand side been cancelled out, but nevertheless, on the top and the bottom, they are not cancelling each other. Does not cancel each other, because we notice chlorine have a higher electronegativity compared to hydrogen. So the attraction force is actually toward to the downward. So the mu is not equivalent to 0. Therefore this is a polar molecule. So guys, please take note, the molecule that are sitting beside on the top and the adjacent side are very important to determine the polarity of the molecule. So then next will be a few examples. Let's say you have a water, this one more water molecules. Those are the electronegativity. Let's check the structure. Of course you need to draw the structure first. First of all, you draw the structure, then from the structure you can determine the polarity. We notice oxygen is more electronegative than the hydrogen, so the attraction force is to here on this side, and on the left hand side is the attraction toward to the oxygen as well. So what will be the resultant? The resultants of these attractions, it's going to be upward. This will be your net dipole moment. The net dipole moment, since there is the attractions, so the net dipole moment is towing to upward, stand for the mu is not equivalent to 0. So it is a polar molecule. More examples, then you can have a look, you can predict. So have a look, more examples. So this is how we predict. So that will be the answer. So you need to know either a molecule is a polar or non-polar. So this is a very good examples. If you have this molecule, the attraction force. Of course, we are looking for the attraction force. Which one is stronger attractions? Over here there is an attraction force, then they are not cancelling each other, therefore we call it a polar molecule. But over here, this is your Lewis structure, this is your according to VSEPR models, then you get the trigonal planar, this is trigonal band, so it's cancelling out each other. So this been cancelled out by this, and the resultant force or resultant the mu is equivalent to 0, and this is a non-polar molecule. More examples are both are linear. CO2 and OCS are both linear. Why this one is a non-polar and this one they asking about polar? This is must look at that guy. This happened due to different in electronegativity, definitely. So bingo, that's the answer, because we notice at this side the electronegativity for CO2 is been cancelled out on left hand side and right hand side, but now therefore and therefore this have a mu equivalent to 0, but over here it doesn't cancel out each other because there is a dipole moment. Okay, it's not enough two bond to moment point in opposite directions, they are not of the same magnitude. Of course they are cancel out each other, but there is oxygen is more electronegative than the sulfur, so they are not and the same magnitude, the attraction force. You remember guys, in order to really understand this one, you try to think this in the term of physics concept vector and do not cancel out. So since they have different in magnitude and they are cannot cancel out each other, therefore this is a polar molecule. So I think that's all for these sections. Stay tuned with my video, I will upload more for your reference. Thank you for watching. Please like and subscribe.